Assalamualaikum and a very good morning. I am Khairunnisa Khairudin and the title of my research is Degradation of Polystyrene Microplastics from Aqueous Solution via Bismuth Magnetic Microswimmer. Microplastics are emerging pollutants that present in water bodies. It comes from industrial and urban area. Previous study reported that approximately 1,000 until 10,000 particles of microplastics in one of the seas in China. It consists of plastic film, containers, microbit, microfibers, and microfragments. The ability of microplastics accumulating chemical additives worsen the impact on the low-trophic aquatic life that ingested the sinking microplastics. This study proposed to degrade the submicron size of microplastics via microswimmers. Microswimmers is a micron-sized machine that has autonomous motion that can be activated through light activation, fuel activation, and external magnetic force. In this study, bismuth-based microswimmers is desirable since it has low band gap, excellent chemical stability, non-toxicity, abundance, and low cost. Moreover, it has been used widely in pollutant degradation such as formaldehyde and phenol. Common element used in microswimmers is titanium dioxide since it has low toxicity, inexpensive, chemical stable materials. However, it has poor light absorption properties, wide band gap, and can need to be activated by UV light. Moreover, metal-coated approach to induce different concentration gradient to propel the microswimmers has its own drawbacks since it needs to include noble metal which are expensive and requires complicated fabrication methods such as electron beam evaporation and sputter deposition. The idea of this study is to induce the movement of the microswimmers through visible light activation and asymmetric shapes of the microswimmers. Hence, bismuth oxyiodide is chosen since it has wide absorption spectrum, low band gap, visible light can be activated by visible light. Moreover, a symmetric shape of the microswimmers itself exclude the coating of noble metal and can be produced using simple setup hydrothermal method. Moreover, this study used magnetic nanoparticles as the additional features of magnetic properties. Hence, it can be recycled. The first objective of this study is to synthesize and characterize the physical-chemical properties of the visible light-driven bismuth magnetic microswimmers. This figure shows the bismuth magnetic microswimmers were synthesized via hydrothermal method. Prior to that, the magnetic nanoparticles were synthesized using one-pot solution method and the iron oxide was synthesized using co-precipitation method. This figure shows the absorption spectra of bismuth microswimmers and bismuth magnetic microswimmers. It can be observed that both microswimmers absorb a visible light range and band gap value of 1.9 electron volt and 1.85 electron volt. Meanwhile, magnetic nanoparticles also can absorb visible light range, wavelength, but has a higher band gap which is 3.2 electron volt. This figure shows the morphology, element, and particle size distribution of the magnetic nanoparticles and microswimmers. It can be observed that the magnetic nanoparticles have a spherical shape with an average size of 0.17 micron. Meanwhile, bismuth microswimmer has a plate-like shape with a smooth surface and the average size of 3.944 micron. Whereas bismuth magnetic microswimmers has a rougher surface with the magnetic nanoparticles coated on the surface, and the average size obtained is 3.913 micron. This figure shows the EDX mapping and composition of bismuth magnetic microswimmers. It can be observed that each of the elements is well distributed, with the highest composition of bismuth followed by iodine and oxygen. The lowest composition is iron. This figure shows the hysteresis slope of the magnetic nanoparticles and bismuth microswimmers. Meanwhile, this figure shows the pro-diameter distribution. It can be observed that the bismuth microswimmer exhibit type 3 hysteresis slope, whereas magnetic nanoparticles and bismuth magnetic microswimmers exhibit type 2 hysteresis slope. It indicates that the bismuth microswimmer are made of non-porous solvent. It can be seen it has a very low volume of pore diameter ranging from 0 until 50 nanometers. Meanwhile, magnetic nanoparticles and bismuth magnetic microswimmers has a mesoporous structure and has a higher volume in size ranging from 0 until 50 nanometers. The BET surface area also supported this finding, since magnetic nanoparticles has a very high surface area, and the surface area of bismuth magnetic microswimmers is slightly increased than the bismuth microswimmers. From the XRD analysis, it can be observed new diffraction peaks on the bismuth microswimmers indicate the presence of iron, and bismuth magnetic has a crystalline structure. The second objective of this experiment is to determine the motion velocity of the bismuth magnetic microswimmers. The motion analysis was done through this experimental setup. The first equation is used to calculate the mean square displacement. Meanwhile, the second equation is used to calculate the diffusion coefficient. From the mean square displacement and diffusion coefficient value, equation 3 is used to calculate the velocity of the microswimmers. This figure shows that the microswimmers move forward in y-axis and left and right in x-axis, exhibit translational propulsion. Moreover, the mean square displacement plot figure shows parabolic curve that indicates the nonlinear motion of the microswimmers. This table shows that the bismuth magnetic microswimmers can move at a reasonable velocity at lower light intensity as compared to previous studies. This figure shows the photocatalytic decomposition of hydrogen peroxide into chemical species, which is water molecule, oxygen molecule, and anion species via light activation. Due to its irregular shape, different molecular concentration gradient was generated, hence propel the microswimmers forward. The third objective of this study is to investigate the photocatalytic performance, kinetics, stability, and recyclability of the bismuth magnetic microswimmers. From the total solution mass loss, it can be seen that the total solution mass loss increased gradually over time. This is supported by the reduction of the total organic carbon and the increment of the carbon dioxide release over time. This figure shows that the percentage removal of polystyrene microplastics in the absence and the presence of microswimmers. It was observed that bismuth magnetic microswimmers can remove the highest percentage of polystyrene in 24 hours, which is 56%. Then the effect of the irradiation time was studied by degrading the polystyrene microplastics in the interval of 24 hours until 120 hours. However, there is no significant difference in the percentage removal in the 24-hour interval. It can be concluded that the polystyrene can be degraded quickly within 24 hours. Meanwhile, this figure shows the degradation plot of polysaccharide microplastics, and it shows an exponential curve graph pattern. Hence, it is fitted to the first order kinetic, and it was observed that polystyrene can be degraded at the rate of 106 multiplied by 10⁻⁴ per hour. The photocatalytic degradation pathway of the polystyrene microplastics were investigated through FTIR spectra, UV-vis absorption spectra, and radical scavenging experiment. From the FTIR analysis, it was observed that after 8-hour degradation of the polystyrene microplastics, new hydroxyl group was observed in the form of polymer hydroperoxide. Meanwhile, carbonyl group was observed in the form of carbonyl compound, and alkene C double bond C bond and conjugated C double bond C bond was observed in the compound of alpha methylstyrate. This is supported from the UV-vis analysis, which new metal group peaks was observed at wavelength of 250 nanometer, which indicate the presence of alpha methylstyrene. The radical scavenging experiment was performed to identify the main active species in degrading the polystyrene microplastics. It can be observed that in the absence of scavengers, the polystyrene microplastic can be degraded up to 56%. However, when parabenzoquinone was added, the percentage removal can only achieve 50%. And when potassium dichromate was added, the percentage removal can only achieve 70%. It can be concluded that superoxide anion and electron are the main active species in degrading the polystyrene microplastics. The polystyrene microplastics were degraded through photocatalysis mechanism and produce intermediate products such as polymer hydroperoxide, carbonyl compound, and also alpha methylstyrene and carbon dioxide molecules. This figure shows the recyclability performance of the bismuth magnetic microstreamers. It can be observed that the bismuth magnetic microstreamers can be recycled until fourth cycle with the reduction of 33% percentage removal of polystyrene microplastics. The table shows that there is slight leach of bismuth and iron. The leach of bismuth and iron is still below the allowable limit, as for iron is 0.3 mg per liter. Meanwhile, for bismuth is 0.5 mg per liter. It can be concluded that the mesoporous structure, crystalline structure, and asymmetric flake shapes of bismuth magnetic microstreamers were synthesis, and it can move at 3.05 microns per second through self-diffusion phoresis. It also can degrade the microplastics quickly in 24 hours, and the microstreamers can be recycled 4 times. This is my Gantt chart this is the Gantt chart of my research, and I have finished my research and finished writing my thesis and have submitted to IPSIS and currently waiting for Senate letter. Meanwhile, this is some achievement from this study. One publication in Journal of Environmental Chemical Engineering and win a gold medal in the Indonesia Inventors Day 2022. Okay, that's all from me. Thank you.